Okay, we'll go ahead and get started here. For those that are logged in right now, welcome to our Tech Tuesday. My name is Jeff Berger from Loy Instrument, and today we're going to talk about PID process control basics. So this is a very basic introductory class. We do have a more expansive class that we offer here at Loy Instrument that covers about a full day workshop with labs. But this is just I guess you'd call it like a process control primer that basically touches on high-level stuff pertaining to PID control, analog inputs, analog outputs, and then the actual process controller itself. So today's session is being recorded. We will have this on YouTube, on our YouTube channel, and I'll send out the link after we get done today. But with that, let's go ahead and get started, and probably take us about 45 minutes to an hour, and then we'll finish up today with some questions and answers. So let's talk a little bit about the agenda. We're going to go through control loop basics. We're going to talk about inputs, terminology around a control loop, current proportional output, on-off output, time proportional, position proportional, and then we'll follow up with a little bit more of an elaborate type control scheme, which is either a duplex output or a simplex output. And then last but not least, PID basics. So this is going to be talking about tuning of a process control loop. We'll be talking about proportional band gain, rate, and reset, and how they interact with each other. Today, PID controllers can range in a lot of different forms. It can be single loop controllers like these UDC controllers that you see at the bottom. There's also other manufacturers like Eurotherm, Yokogawa, Watlow, Omron. There's a lot of different single loop process controllers out there. And then also it could be either a hybrid controller or a PLC that does your control. So this would be like a PLC, like an Allen Bradley, a Modicon, a Siemens, or a HC900 from Honeywell. So there's a lot of different forms of PID controllers out there. Today we're going to talk about some general terms that should apply for each one of these different controls out there in your plant floor. So what is process control? So we'll start with a very high-level overview of what process control is. Process control is a method of maintaining, applying a controlled force to materials. It's also maintaining a controlled environment for materials or personnel, maintaining safety in a hazardous condition. It's essential for the quality control of a product and also for controlling cost of manufacturing. So if you have a very good process control scheme out in your plant, on your plant floor assets, maybe it's a furnace, maybe it's a room where personnel are actually doing the work. It could be you could be controlling temperature on a vat of liquid or chemicals. But in order to control the quality of the product and cost of the manufacturing of the product, PID control is essential in today's industrial plant floor control. PID control is used in everyday products. So for example, it can be your home heating and cooling system. So your controller would be your thermostat, and your thermostat has a temperature sensor hooked up to it. It also has an output to a on-off gas valve that's providing gas to a burner that turns it on and off. Or it could be up to your cooling system, which turns on your air conditioning on and off. That's a very, very basic form of PID control. Your refrigerator, your stove, even your dryer, your clothes dryer has a very simple form of on-off PID control. You also have a pretty elaborate PID control system in your cruise control of your car. So when you think about it, when you're setting your cruise control, let's say 60 miles per hour, or like my wife at 80 miles per hour, the cruise control in your car is trying to control the set point, which is what your speed is at. So if it's 60 miles per hour and you're coming up to a hill in the expressway, your gas pedal knows to give it a little bit more gas to maintain that 60 miles per hour going up the hill. and then when you get to the top of the hill, it releases that gas pedal to maintain 60 miles per hour. This is a cruise control in cars have had PID for years and years, and it's a pretty elaborate form of PID control. So taking that one step further, when you think of it as in simple terms of a PID control system, now you can adapt that to the industrial applications. So when you take a look at controlling temperature in ovens, furnaces, kilns, it might be a batch application. In the glass industry, you have big, large ovens, curing ovens called Lears, four hearths for melting the glass. Almost any application on your plant floor where you're trying to control something, whether it be flow, level, temperature, pressure, probably has a PID control system or PID controller somewhere in that loop. So let's talk a little bit about the three things that are needed for a control loop to work effectively. The ultimate goal from today's short session is if you could go out on your plant floor or when you're visiting your customer doing service, try to identify these three things. When you get a good rounded view at a control system, it is always going to incorporate these three things. So when you're doing troubleshooting or when you're adding a control loop to something out in the field, you want to make sure that the three components include an input, controller, and output. So the input can be what you're measuring the flow or temperature or pressure of the system. In this case, I have, we're going to be measuring temperature. So I have either an RTD, which is a resistance temperature detector, measuring temperature, or I have a thermocouple, which is thermocouple based on the temperature range that you're trying to measure. We'll get into a little bit more about the thermocouples in a couple slides here. Or it can be a transmitter. A transmitter would be typically considered a high-level input. That would be a 4 to 20 milliamp, a 1 to 5 volt, 0 to 10 volt, or some other voltage that's linear to the process signal that's feeding it back to your control loop. The second would be your actual controller itself. This would be your PID controller. So like I was saying at the beginning, it can be either a single loop controller, which is a small quartered in or eighth in controller that's on the front of your panel door, which is displaying your actual temperature and your set point. It could also be a hybrid control like the HC900 or a PLC that you might have on the plant floor. This is really the heart of your process control loop. This is what's taking the input, which is your process variable, measuring it to your set point, and then adjusting your output of the control loop so that it can maintain that set point. Last but not least is your output. Output can be in a lot of different forms. It can be an actuator that's controlling gas that's supplied to a burner. It can be a process control valve that's controlling the flow or level or pressure of the system. Or it can be an SCR, which is basically an electric heating element system that controls electric heating elements and voltage to the elements to be able to control your temperature out in the process. So there's a lot of different forms of outputs. We're going to get into a little bit more explanation on each one of those forms of output. But these are the three things that make up a control loop. This would be considered a closed loop control system. So the input feeds the process variable to the controller. The controller matches that to set point and sends an output to the actuator or valve or SCR that's controlling the system, and then inadvertently then is going and altering the input so that it can get back up to set point. So this would be considered a closed loop control system. This is probably 99% of what you have out in your plant floors that is controlling a lot of your systems out there. So process control requires a measurement system, which is your input, a comparing system, which is your controller or PLC, and then an output to affect that process variable, which is your main control output. The measuring systems today can take on different forms. It can be a mechanical measuring system. For example, if you had a system that was a pneumatic system, or call it a filled system. Filled systems were sensors that had an oil-filled leg that when the temperature would increase in the oil-filled leg, it would put pressure on some bellows that would inadvertently affect the controller. It could be a helix tube, which is sensing pressure, and as the helix tube increases in pressure, it straightens out the helix tube, which would move a needle and then affect the control system. These are typically older systems. You don't find too many of those anymore. The only time you really find mechanical type measuring systems is probably in a explosion-proof area where you can't have electromechanical or digital signals. But most of the time, customers are usually using electromechanical or a digital signal fed back to the control system to do the control. But these three systems here are basically your temperature sensors or process sensors that are feeding the signal back to the process controller. The most common sensor out there that we come across are thermocouples. Thermocouples has a millivolt output proportional to the temperature that you're measuring. They're very accurate. They are fail-safe. If the thermocouple opens, the temperature should go upscale, causing your PID control loop to shut down your output. You're typically going to want to select the type of thermocouple that matches your temperature range. So there's many different thermocouples based on the temperature range that you're trying to achieve and the accuracy that you're trying to achieve. We're not going to get into all the different types of thermocouples today, but the way that the thermocouples work is two dissimilar metals, and when these two dissimilar metals are joined together, heated up creates a millivoltage, which is kind of crazy when you think about it, that just two wires joined together can create a millivolt signal when they're heated up. But many years ago, a smart man actually came up with that and put that out there in the industry, and is used quite widely throughout a lot of the different industries that we come across. The one thing to make sure of on a thermocouple is make sure that your extension wire that you have going from your thermocouple to your process controller is the same type of extension wire as the thermocouple that you're using. So you want to carry those two dissimilar metals all the way through the system, all the way back to the PID controller that you have it hooked up to. If you don't do this, it can introduce a lot of variations to your process signal, and it creates a lot of error. So this is one of the things that we see commonly happen out in the industry when new extension wire has to be run. Sometimes customers will just use copper wire, and you have to make sure that you don't do that, that you actually use the thermocouple extension wire that's matching your thermocouple. Here's a diagram of how a thermocouple works. At the very end, you'll have your hot junction. Basically, this is where the weld is, where it joins the two dissimilar metals. This is the measuring point that it's measuring your temperature. Back at the connection to the head of the thermocouple, you have a connection where then you connect up your extension wire going back to your controller. And this is a diagram of a controller just basically reading out millivolts. But back at the controller, you'll have another connection, which is commonly known as your cold junction connection. Back at the these would be on the terminals on the back of your controller or PLC. And of course, you have your extension wire that runs in between your thermocouple and your controller. So a lot of different styles of thermocouples. You can have thermocouples with cast iron heads, aluminum heads. You can also just have a quick junction connection on the outside to make it easy to replace the thermocouple if one goes bad. There are a lot of different protection tubes based on what type of application you're putting the thermocouple in. You have ceramic tubes, Inconel tubes. We can help you define what type of tube you might need for your process if you have an application that is eating away at the thermocouple and needs a little bit of protection there. But there are a lot of different styles of thermocouples. Inside of the head of these thermocouples is where that junction is made with your extension wire to take it back to the controller. Typically, this is where we're doing our calibrations. We'll unhook the extension wire from the thermocouple and place it on a calibrator and send a signal all the way back through the extension wire to the controller to check out this calibration and do troubleshooting that way. So thermocouple components, like I said, there's a lot of different styles of thermocouples, thermocouple wells. You can have a cast iron or aluminum head to protect the junction at the top of the thermocouple. There are quick connections or quick panel jacks that you can actually have on the outside of your control cabinet that would allow easy connection or calibration connection to the system in order to allow the outside service company to be able to go in and do calibrations without having to open up your control cabinet. We usually recommend this a lot, especially in applications where you require some type of shielding or protective gear to open up the cabinet. This allows a technician to be able to do troubleshooting and calibrations without opening the cabinet by connecting into these jack panels. The other connections that you can have are male and female connection plugs. Again, these connection plugs need to be the makeup of the thermocouple that you're using out on the plant floor. So if you're using a type K, these plugs need to be type K. Likewise, if it's S, J, T, or some other thermocouple, you have to make sure that those are the same makeup with the two dissimilar metals. RTD is another form of a temperature sensor that you can have hooked up to your PID controller to sense temperature. The RTDs are typically a little bit more accurate than the thermocouples, but the temperature ranges are typically a little bit less as well. So you can see here that we can get RTDs that will go from -300 to 1200 degrees. The RTDs do come in a lot of different forms, but the principle behind an RTD, it has a resistive temperature detector inside of the RTD, where as the temperature increases, the resistance increases as well. And it is a somewhat of a nonlinear signal going back to your controller. So when we do these type of calibrations, we usually have a handheld calibrator where we can dial in the resistance, or a decade box, which we used to use way back when to calibrate these type of systems as well. But typically you'll either see a 2-wire, a 3-wire for long distances with the lead length, or a 4-wire in some cases for these RTDs. So the RTD, again, basically is a resistance temperature detector. In some cases, it has 2 wires going out to the temperature detector, providing a resistance back to the controller. And then the controller will actually take that resistance and extract what that temperature is from that resistance that it's measuring. Some cases, what they'll do is they'll add in a 3rd wire. And for applications where you have long leads, you have to compensate for that lead wire length and the resistance that lead wire length has. So you will actually have a 3rd wire that goes back to the controller to compensate for that lead length. Most typically, those wires are 2 red and 1 white, with a positive and negative, and then a compensator for the long leads. Another sense of a way of sensing temperature or process value is with an optical pyrometer. And this is a non-contact type of temperature sensor that basically can measure the temperature of a process using an IR or some other type of optical detection of the process to see what type of temperatures there are. It sends a millivolt signal or a 4 to 20 signal back to your controller in relation to whatever the temperature is in the process. These are typically very high or extremely high temperatures. I've seen a lot of these used like in the steel industry where they're measuring molten steel, or in the glass industry where they can't actually put a thermocouple in contact with the process because of the temperatures are too high, and the thermocouples wouldn't last very long in those applications. So any type of non-contact, high temperature type of sensing, the optical parameter is usually the way to go. Now likewise, although these are used in high temperatures, they're not typically used at a very low temperature. So these usually start working 300 to 500 degrees on up, and they're not used for any low temperature sensing. Last but not least is another form of measuring the process value is using a transmitter. So in some applications where you're trying to measure a liquid level or a flow, it could be a pH or a relative humidity or dew point. In some of these applications, it requires a pressure transmitter or a flow transmitter to have the capability to measure that process value and then send that signal, the proportional signal of a 4 to 20 milliamp, back to the controller to provide that process value. Typically on those type of transmitters, that 4 to 20 milliamp signal can run very long distances. So if you have a process controller that's 1,000 feet away from the process, and say for example you used to use a thermocouple, instead of running all that extension wire all the way back to the controller, you can use a temperature transmitter, which would still have a thermocouple hooked up to the transmitter, but then would convert that signal over to a 4 to 20 milliamp to be able to run at very long distances. The other benefit of using a transmitter in those applications is if you run a 4 to 20 milliamp signal, it's a very low signal, and it's very it has great noise immunity as well. So if you're running long distances, need a very accurate signal that has high noise impedance, then you probably want to look at a transmitter in those type of applications. Transmitter can be used for temperature. You can hook it up to a thermocouple. You can actually have a pressure transmitter, a smart transmitter, a level, flow, and many other variables that you can convert over to 4 to 20 and use in a transmitter for those type of applications. These are typically a little bit more expensive than your typical thermocouple or RTD, but again, for applications where you need very high accuracy, long distances, or if you're measuring pressures, levels, or flows, this might be the product you want to use in those applications. I was talking about how a temperature transmitter is linear. So say for example we had a type S thermocouple, and we had it range from the transmitter range from 1400 to 3000 degrees. This is a representation of how that milliamp would change, or how that signal would change along with the temperature. So if we set up the low end at 1400 degrees, that would give us a 4 milliamp signal, and then 2200 degrees, 12 milliamps, and 3000 degrees, 20 milliamps, and then proportional anywhere in between there. If you're using a transmitter, you typically have a 250 ohm or a 500 ohm resistor either built into the controller itself or actually mounted on the back of the controller. So this is one thing to make sure when you're installing a transmitter that somewhere in the line you do have a 250 ohm resistor or a 500 ohm resistor, depending on the controller, to be able to convert that signal. A couple pictures of some temperature transmitters. So this one has a display with a thermocouple in a thermal well mounted in and then wired into a display that also puts out a 4 to 20 milliamp. So it gives you a local readout. Some applications this is good because if you're trying to troubleshoot a system and you have a PID controller hooked up to a temperature sensor that's clear across the plant, it's good to have an indicator right at the sensor so that you can do troubleshooting right there, and you not have to walk back and forth between your controller and your sensor. There's also these are called hockey pucks. These are 4 to 20 milliamp transmitters that are actually mounted right inside the head of a thermocouple, and your thermocouple would be connected to this hockey puck, and then this hockey puck would actually send out a 4 to 20 milliamp back to your control system. We talked about transmitters being able to offer static pressure, differential pressure, liquid level. All of these provide a milliamp feedback into your control system. Just one other thing I wanted to add on each one of those sensors that we talked about. That's really the critical part of your control system, is providing an accurate signal back to the controller so the controller can do its control. If you don't have an accurate input, the controller is only going to control to what that input is providing to it. So make sure that if you have thermocouples that you're changing those out periodically. You do have to change those out every once in a while based on how many times you go above a certain temperature. The resistance of those thermocouples will start breaking down over a period of time, and then it will get to a point where it'll actually fail open, allowing you to not be able to do process control. So make sure that your thermocouples are changed periodically. Same thing with your RTDs. Transmitters, make sure that those are calibrated periodically to make sure that you're getting a good signal back to your controller. Now we're going to move on to the final control devices. These are the devices that are actually going to do your control. So once the controller receives the process variable from your sensor and compares it to a set point, it's going to make a determination on what level of output to provide the system in order to change that process variable. These are some pictures of some different final control devices that are out there in the field. We have a mod motor up here at the top right-hand side, which is pretty commonly used on butterfly valve applications where you're controlling gas flow to a burner. It can be controlling dampers hooked up with a linkage assembly to control airflows and things of that nature. On-off contactors, so in an on-off or time proportional output, you can have contactors turning on and off voltage to electric heating elements. Solenoid valves that control gas flow or water or liquid flow. And then process control valve positioners, which are typically used on applications where you're trying to control a flow, you're trying to control a level of a tank, things in that nature where you actually need to turn on and off a process control valve like a globe valve or a sliding gate valve in order to control those. So these are a lot of different forms. We're going to talk in a couple slides here. We're going to talk about the different types of control outputs that control each one of these devices. But for right now, we'll just leave it as these are some of the devices that are used out in the plant floor in order to control your process. So last but not least, we're going to get into the control loop itself. We talked at the beginning about closed loop control systems, and this is the primary focus for today's session. In a closed loop system, it completes a signal path in a control system. It feeds back the process variable to the controller, controls it to set point, and then provides an output to be able to control the process. Some of the terminology that is pretty common out in the industry that you're probably going to hear at some point or another. The very first one is PV. This is your process variable. This would be like on your home thermostat. This would be your actual temperature that you see on your thermostat. If you're like my house, my family likes to turn that temperature up super high during the winter and basically roast me out of the house. Me, I like to have it a little bit cooler, and sometimes my family doesn't like that. But In the thermostat, this would be your actual temperature that you're seeing on the thermostat. In the industrial environment, this would be your quartered-in controller or your PLC panel that's actually showing the actual temperature. This is known as the process variable. The next terminology here that's very important is your set point. Obviously, when you have a furnace in your plant or some other type of control loop, the set point that you control the process at is very critical. A lot of different applications and plants have different set points that they control at, but from a safety, from a quality standpoint, and for a cost control standpoint, the set point control is very critical. So set point is what you're going to control to, and the process variable in an ideal world should match what that set point is. Error is when you take your set point minus your process variable, and whatever that equation equals, that is your error. The controller's primary function is to reduce error. So if you have let's say you have a batch furnace, heat treat furnace, and you open the door or open the lid on the furnace, and you inject some type of disruption into the process, you typically would see that process variable dip, and the controller is going to try to do everything it can do to increase that output in order to get the process variable back to equaling the set point, ultimately reducing the error. So it can either be a cooling system or a heating system. Both are working towards trying to reduce the error. So let's talk a little bit about heating and cooling systems. In the PID world, there are two types of outputs. There's reverse acting and direct acting. In the reverse acting, as the input signal decreases, the output signal would increase. So for example, again, if we had a heat treat oven and we were trying to control at 800 degrees or 900 degrees, and we open the door into the putting parts into the oven, what would happen to the process variable? It probably will start decreasing. Well, when the process variable starts decreasing, the control output on that PID controller will start increasing to try to compensate for that signal going low and bringing it back up to set point. Typically, the reverse acting is always used in heating processes. Now, the opposite of that is direct acting. Direct acting is always used in cooling type systems. So in this, it's just the inverse that happens. If the input signal increases, so does the control output, trying to get more refrigerant to the process in order to cool down the process. So for example, you go to your refrigerator, you open the door, what happens? The temperature inside the refrigerator starts increasing. Well, in order to get that cool again, what does it do? It turns on the compressor, starts feeding the refrigerant to get that temperature back down, and that would be known as a direct acting system. In the industrial world, there are a lot of applications that will use reverse and direct acting in the same PID loop. For example, in a duplex system, you might have 0 to 50% on the PID controller working as a cooling system, and 50 to 100% on the controller working as a heating system. We'll talk a little bit more about that. It's a little bit more of an intricate type of control algorithm, but just know at this point that reverse acting is usually used on heating systems and direct acting is used on cooling systems. We talked about analog inputs. When we refer to analog inputs in a PID system, typically thermocouples, RTDs, transmitters, things of that nature. Deviation is the next terminology in a PID system. Deviation is basically your error signal. So if we have a set point of 1,000, process variable at 900 degrees on our controller, we have a deviation of 100 degrees. So the deviation, again, in a PID algorithm or a PID scenario is the error signal that's created with the process control loop. Feedback is basically the terminology that's used for feeding the process variable back to the controller. We usually use this feedback in the form of an input signal, an analog input. Again, can be a thermocouple, transmitter, something along those lines. Output. Output on a controller or a PID controller is the result of the deviation that we see from the set point and process variable. In most cases, probably 90% or so of those cases on a PID controller, that output is going to be represented as 0 to 100%. Sometimes you'll see it extend beyond the 0 to 100%. It might go -5 to 105%, but most cases 0 to 100. That output for reverse acting, 100% would be full heating, and 0% would be cooling or no heating. Next, we're going to talk a little bit about the control forms coming off of a PID controller. So if we're building up our scenario here, we have an analog input, which is providing feedback to the process controller. And then the process controller is taking the set point, matching up with the analog input or the process variable in the controller. And if there is an error, the controller sends out an output to the final control device to control the system. The most simplest form of control output is on-off. So what I mean by this is the PID controller has a relay on the back of the controller, and if it needs heating, it turns on the relay, closing contacts to be able to control a solenoid valve or a contactor or some other means of controlling the heat. And when you are at 0% output, it turns the heat off and allows the temperature to come back down. This is usually used in applications where you don't need real tight process control. You might be able to live with a little bit of swing above and below the set point. Most times it's used on applications just like we were talking about at the beginning at home. It can be a furnace, you know, when the temperature goes above your set point on your thermostat, turns off the heat. When it goes below the temperature on your thermostat, turns on the heat, and it's just an on-off application. So again, very simple type applications, on-off. Can also be used, you also use on-off if you have a limit controller on your process, which needs to be factory mutual with a manual reset. This would be more of a safety type of system versus a control system. But the most simplest form is on-off at this point. We'll keep it at that. The next type of control form, which is a little bit more elaborate, is proportional. And this would be for systems where it needs a little bit better accuracy, a little bit better control of your process variable, the set point. And would typically, the controller would send out a proportional signal, which is proportional to the output of the controller. In most cases, it's either going to be a time proportional, which is a pulsing type of output, or it's going to be a 4 to 20 milliamp output, which again is proportional to the output of the controller. In these cases, when you use current proportional, if you take 0 to 100% out of the controller and you have 4 milliamps at 0 and 20 milliamps at 100% and proportional anywhere in between, this can provide a signal to a lot of different control devices out on the plant floor that allow that type of proportional system. Very good process control, very tight process control, as long as the loop is properly tuned. Different forms of the, as we talked about, on-off, proportioning, these are the two different types of control forms. And in either system, we're still incorporating this terminology that we talked about earlier. It still has a process variable, which is your actual measured variable, your set point, which you're trying to control to, the deviation, which you're trying to eliminate, and the output, which you're trying to use to control the control system to reduce that deviation. If we looked at the on-off control in a graph type scenario, on the very bottom here, we have our process variable range. In this case, we have 0 to 600 degrees. And over on the left-hand side, we have, whoops, let me go back there real quick. On the left-hand side, we have a 0 to 100% controller action. All right, so if our set point was 300 degrees on an on-off control system, we would build into the controller a little bit of hysteresis above and below that 300 degrees so that our relay is not chattering on and off. But let's say in this case, we had a 10% hysteresis band above and below set point. You can see as the temperature increases, we want to shut off the output. And as our temperature decreases, we want to turn on the output. And there is nowhere in between that this is proportional. So either you're going to get 100% control action on or 0% control action off based on where your process variable is at compared to your set point. So this is a good depiction of what an on-off control system would look like. Here's another graph here, or not a graph, but a picture showing a little bit about what a typical on-off control system would look like. In this application right here, we're controlling gas flow. So we have a valve here. It can be a butterfly valve. It can be a solenoid valve. This is the output. And then we have our input, our analog input, which is this flow transmitter. And some cases on-off, it uses 2 relays. Some cases it just uses 1. But this would be an example of a process control loop with your input, controller, and your output. The next step of a little bit more of an elaborate type of control output using on-off still is called time proportional. This is a control output algorithm that would allow you to have a little bit better control of your process using the tuning features in a controller. The way that it uses the time proportional is it pulses the on to off transition out of the controller to the final control element. The way that we do this is in the controller, you would set up a pulse time. So let's say, for example, in this situation, we used 60 seconds. So as the controller output changes to try to eliminate the deviation between set point and process variable, as the output increases, so does the on time of our relay output. So for example, if I had a 60-second time and I had 100% output, that means that the output would be on 100% of the time. If the controller output reduced to 50%, then my cycle time for my on to off transition would be 30 seconds on and 30 seconds off. This would be known as a pulsed output. And then anywhere between 0 to 100%, that 60 seconds would be proportional. So as my output increased or decreased all along the 0 to 100%, my on to off time would change according to that output. This would give you a little bit better process control if you had an on-off type situation, and all you would have to do is set up the controller for time proportional and tune the control loop in order for it to operate this fashion. The next that we talked about was proportional control. Now, if we put proportional control on a graph with the process variable being at the bottom and your output of the controller on the left-hand side, you can see now that it's more of the transition from on to off is very linear from 0 to 100%. So if our set point was 300 degrees and our actual process variable started inching upwards or downward along this graph, you can see that the output is going to change according to where it needs to move that process variable back to equaling set point. So at a 4 to 20 milliamp output out of a controller, this would show you that 0% would be 4 milliamps, 100% would be 20 milliamps, and then it would try to control that process variable for your set point in a linear fashion. Proportional control is going to offer you the best control over your application. It gives you a very good accuracy and controllability of the process. So this is an example of another control loop here using current proportional output, which we just talked about. The current proportional output, which would be your 4 to 20 milliamp, would go to your final control device. And based on what your set point was and what your feedback from your transmitter was, it would actually open and close this valve proportional to where it needs to control at. Like I said again, you can have 4 to 20 milliamp signal, very long leads. So if your final control device was quite a distance from your control panel, it would be able to carry that signal pretty good distances there. The last type of proportional control, which I'm gonna mention, even though it's really not used widely in the industry. I mean, probably back 30 or 25, 30 years ago, this used to be a widely used control output in the industry called position proportional. In this type of system, this was used a lot in the steel mills. It's actually used somewhat in the air makeup units in today's world. It's called Series 90 control with a feedback of about 135 ohms. But in most cases in industrial plant floors, the final control device, which would be your actuator, your valve, damper actuator, would provide 3 wires back to the controller that would have a 0 to 1,000 ohms or a 0 to 5 volt signal that would be linear to wherever this position of this valve was. So if the controller was asking for 50% output, then the control device, hopefully it's at 50%, would send a signal back to the controller saying that either I'm at 500 ohms or 2.5 volts to equal that 50% output that it's calling for. The output form out of this controller is basically an increase relay and a decrease relay that's controlling this actuator and offering a small feedback loop into the controller saying, yes, I'm at 50%, you can stop calling for an increase or decrease in signal. And there's a lot of different troubleshooting that you have to do and maintenance that you have to do on these type of systems. Since it does have a slide wire that's built into the actuator offering that position feedback, you have to make sure that those slide wires, if they're old, that the slide wires are clean, free of dirt, so they get a good signal back to the control system. And you also have to make sure, obviously, that in order for this system to work, that you do have a signal that's not open, but that's actually making contact, providing that feedback circuit to the controller. So again, these type of systems were initially used in pretty harsh industrial environments that probably were not suitable for a slide wire inside of an actuator because they would get pretty corroded and dirty over time, and the feedback signal would start hunting back and forth, causing some pretty erratic control systems. But with the invent of 4 to 20 milliamp output, a lot of these position proportional type control solutions have gone away over the years. Last but not least, we're going to talk about duplex control. So on a UDC controller, using duplex control, you might have a situation where to control the process variable, you have a cooling loop and a heating loop. In this scenario right here, we're using an airflow for our cooling, and we're using gas flow for our heating. In this type of situation here, over the same 0 to 100% output of the controller, we have actually 2 independent, either on-off or 4 to 20 milliamp outputs out of the controller that will control the heating and cooling. So you can see if we had a graph that was 0 to 100% on the bottom 0 to 50% would be cooling. So that means that at 50%, if I was using a cooling 4 to 20 milliamp output, 4 milliamps would be at 50, 20 milliamps would be at 0. So at 0%, I have full cooling. And then on my heating, which is reverse acting, I have 50% being my 4 milliamp, 100% being my 20 milliamp. So I would have full heating at 100%. Sometimes on the cooling side of it, you'll use a blower or a fan or some other means of controlling the cooling mechanism that cools the process. These are usually used in applications where you have very intricate control systems that require some form of cooling in order to get the process temperature down to a certain point where you can actually get it back to the set point. In some cases, the process control loop has just automatic type of cooling where you don't have to inject a cooling methodology in the control loop, and the process just controls under its own cooling scheme. So, but in some cases, you will need this type of action on more intricate control systems, and again, using two independent outputs out of the controller to control both heating and cooling of the process. We're going to wrap up here with a real quick discussion on PID tuning. So to summarize a little bit, we talked about analog inputs. These are the inputs that's providing the process variable to the control loop. We talked about the controller itself and some of the terminology in the controller. We talked about the output, which actually ultimately controls the process variable and feeds the signal back through the input to the control loop. This is considered a closed loop control system. In most cases on closed loop control systems, you do have to do tuning. Just like the old days when you had to tune your carburetor on your car to get optimal performance, same type of thing on process control loops. There's three different values that you have to change in a control loop when you're doing the initial setup, or if you're doing any major overhauls to your furnace or application out in the plant floor where you would need to retune it. But these three values are proportional band or gain, integral, and derivative. This is known as PID tuning, and these values do need to be set up so that you can minimize any hunting of your process control, overshoot, undershoot of your process variable, and allow you to control right at set point. So let's talk a little bit about how all three of these interact with each other. So the terminology that we're going to talk about is tuning constants, and when I talk about tuning constants, this is the P, I, and D tuning that's in the controller. And then we did talk about control. So in order to get optimal control, where we're trying to reduce the error between process variable and set point, we want to make sure our tuning constants are set up appropriately. When we talk about proportional band or gain, most controllers allow you to configure this one way or the other. Know that proportional band and gain are just the inverse of each other. They both do the same thing in a process control loop. So proportional band or gain is the percent change in the control variable that causes the output to move 100% of the travel. So for example, if I had a setting of a number 1 in my proportional band, and I had the controllers configured for proportional band, this would act just like an on-off control. Because if I'm setting it at 1, that means at 1% change in the control variable, I want that output to move 100% of the travel. So if I had a set point of 1,000 degrees and it went to 1,001 on the process variable, guess what? I would get a 0% output. Likewise, if I moved from 1,000 degrees to 999 degrees, I would then get 100% output out of my controller. So this is the same as an on-off control. Basically, you're not getting any type of linear control output, and you'll probably get some pretty rapid swings of your process variable around your set point. So as you increase the proportional band, it will start leveling out those swings, and your output will become less erratic and be able to change between the 0 to 100% in gradual steps versus slamming it from 0 to 100 and not having really good control. The next is integral. Integral is also known as reset. So as you're configuring the controller and you go into the PID settings, you'll actually see it come up as reset. And on the reset, the way that acts is as long as there's an error between your process variable and set point, reset will start doing its thing. And it will try to reset the output to get back to set point. So if you were just controlling your process with just proportional band alone, and let's say you had a proportional band of 10%, which gives you a little bit of a swing up and down, above set point, below set point. As you start introducing reset, it will actually start minimizing the hills above and below the set point, and eventually bring it back to set point where your deviation is at 0. So as long as there's an error between your process variable and set point, the reset action will occur. Last but not least is your derivative, also known as rate. In most applications when we do tuning, you'll use pretty much no rate to very little rate. What rate does is anticipates the change in your process. So as your process variable starts moving, the derivative action will actually start anticipating that there's going to be a change that's happening, and will start moving your output to compensate for that change. It does not correct for a constant offset, but it's basically an anticipator of change happening. If you add too much rate into your process, you'll get a process that will swing pretty violently up and below the set point, and sometimes not even come back to set point, because you're, as I said before, you're not correcting for any constant offset. It's just anticipating that there's a change coming. So most cases you're going to use proportional band or integral, and like I said, very little to no rate at all. A couple quick graphs here. Proportional band only. If we were to control proportional band only, and we had on the left hand side we have our process variable with our set point. We have our actual red line here is our process variable, and then right below that is how the output is changing up and down in order to control our process variable. If we had proportional band alone, most cases it would probably look like this, where you get a little bit of a cycle up and below the set point that you're trying to control at. If we added a little bit of rate, you can see as the set point and the process variable is actually, the process variable is moved a little bit above the set point because it's anticipating change. And even though it is reducing the cycle below the set point, it's actually with the rate, it's actually increasing the cycle above set point. So you can see as if we were to record this value, you would see the cycle happen, and it would probably move this curve just slightly above the set point. When we add all three, this isn't a really good depiction of optimal tuning, but it will show you that initially, if we only had proportional band, we get this initial swing above and below set point. And then eventually, when we're adding in reset, you should see that process variable come back down to set point and equal the set point and tune or control pretty well after that. The optimum tuning parameters would allow the process variable to come up to set point with very little overshoot or undershoot and control right along those lines of the process variable with no deviation at all.
This is a depiction of somehow, as we add in more reset, you can see here with 0 reset, we might have a system that has the process variable above the set point at all times if this dotted line was our set point. As we add in reset, you'll see we put in 0.5 reset, and when we do that, it starts bringing it back a little bit quicker. 1 reset, a little bit more responsive. 1.5 is good, and then 2, you can see that we have a very rapid control correction at the very top, and then comes along and maintains the set point. Last but not least, I do have kind of a graph here, a visual depiction on bringing all 3 of these together. At the very beginning of this training, we talked about cruise control in your car. And this is probably the simplest way to describe how proportional band, reset, and rate interact with each other, using an example of a Jeep going up a hill that might be on an expressway. This is, again, a very simplified approach. There is a complete math algorithm that you can work out and come up with optimum tuning parameters, or in today's world, a lot of the controllers nowadays have an auto-tune feature, which allows you to press 1 button, the controller figures out its tuning parameters, and away you go. A lot easier than what it was 30 years ago when I first started into the PID world. I had to figure out that all manually, but now they have auto-tune, which is great. So let's take an example of a cruise control. So let's say we have a Jeep that's set at 60 miles per hour. We're going down the expressway, and we need to maintain 60 miles per hour that has a hill coming up at the beginning. So what does rate do? Rate actually starts anticipating that the hill is coming up a mile down the road. So what rate will do is, as it starts to see that process variable change slightly, it will start anticipating that it needs to apply more gas to the engine, putting more pressure on the gas pedal, anticipating that this hill is approaching. Reset happens at the very top of the hill. So as we are going up the hill and we get to the very top of the hill, what would happen if we kept that pedal pressed all the way down to maintain that 60 miles per hour up that hill? If we did not have reset action, we might launch off the top of the hill. Maybe like if you're driving a Jeep or some dune buggy out in the desert and you come up to a hill and you're ramping up the hill, if you kept the gas down, you'd probably fly off the top of the hill. So we don't want to do that. So the automotive manufacturer said, in the control algorithm in this Jeep, we need to add reset action at the very top of the hill so that the controller in the car will take a look back at set point and start resetting that gas pedal so that you maintain that 60 miles per hour without overshoot or undershoot at the top. Proportional band is what the controller is going to be using, or the auto control is going to do on a Jeep, all the way at the beginning of the hill, up the hill, at the top of the hill, and it is going to be watching that 60 mile an hour set point in the actual speedometer and adjusting that gas pedal so that it maintains a certain percentage around the 60 miles per hour. When we talked about the proportional band earlier, obviously if we had a proportional band of 1 on a cruise control in a car, we would either be 100 miles per hour or 0 miles per hour and nowhere in between. So what we try to do is we try to have a proportional band wide enough where it maintains the 60 miles per hour, but gives us a nice slow transition of the gas pedal to maintain that set point of 60. So I use the analogy of the cruise control in the car to really help simplify how the PID works in a PID controller in order to control that set point. Obviously, it can get more elaborate on more elaborate control systems than what I just described, but should give you a pretty good feeling for how PID works in a controller. With that, we're going to wrap up here today with the PID basics. Hopefully that gave you a nice high-level view of PID control and what's all involved in a process control loop. And as I stated earlier, I would challenge each one of you to go out on your plant floor, or if you're a service provider, to go out into the plant process at your customer and identify each one of those, because whether you're doing process control or troubleshooting, you need to know how each one of those interact with each other in order to provide good process control. So challenge each one of you of doing that. At this point, I'll open it up for any questions. If any of you have questions that we can help answer, and then we'll wrap up here shortly. Make sure to unmute your mic there as well if you do have questions. All right, so no questions today, but feel free to reach out to us if you do. And we will also we will have another Tech Tuesday coming up. I sent all the schedules out to you. I don't have that schedule right in front of me, but I will send out a reminder this Friday for Tech Tuesday next week. And as I said, we will also send out the recording that's on our YouTube channel, so feel free to rewind it and watch back the exciting training of PID control. So with that, I hope you have a good rest of your week, and stay safe, and we'll be talking to you soon.